I have to read the spiel if you can hear me. So I'll just start. Okay, thank you very much. Sorry, I forgot it. Host statement. Oh yeah. Here we go. These events are being recorded and will be live on the iQuest YouTube channel. For bandwidth purposes, we would like to request you keep your microphone and video off until the end. Should you have any questions during the presentation, I will watch the chat box and will interrupt the presenter at the appropriate time. Otherwise, please feel free to ask your questions following our speaker's presentation. Thank you. So today we have our own Tom Faulkner presenting. And Tom got his PhD from MIT in 2009, working on applications of ADS-CFT duality to heavy ion physics. He did postdocs at the Kavli Institute at UCSB and at the Institute of Advanced Study before joining the faculty here at in 2014. And now he mostly works at the intersection of quantum information, quantum field theory, and quantum gravity.
Thank you very much. I guess everyone can hear me. So, inviting me to talk. I think talk might be a change of pace from other talks at the iQuest seminar. So please feel free to interrupt me if you have questions. Okay, so I'm going to talk about
there is no sound.
no sound.
Okay.
I've got to speak there. Can you hear me now?
Now I can, yes.
I'm going to speak to this thing, which is going to be quite interesting.
Here, I'll sit right behind it. So you can...
Can't you just use a microphone? I mean, plug it into something, which is more. I cannot hear anything this way. No sound.
Yeah, we had this with the speaker last week, and I had to stand by the little pillar.
Here we go.
Well, you just
Yeah, that's good.
a microphone and plug it into the computer and be done with it. Okay.
Right, this is a complicated setup. I don't want to be messing.
Okay.
Let me try this. I'll try to remember.
Yeah, we need
Okay,
to
so
regain control of that room. That's the answer.
Can you hear me now, Edward?
Yes, I can.
Yes.
So, all right. So this is work. It's funded by a Murray grant under the name Quantum Codes, Tensor Networks, and Quantum Spacetime. And studying is well, in quantum gravity, there seems to be this correspondence between areas and entropies. And it seems to be telling us something deep about quantum gravity, and we'd like to understand that better. So one approach is to study toy models where this is the case, where there is a similar correspondence between area and entropies, and to really, sort of study this toy model in great depth. So in particular, toy models will be studying random tensor networks. And the thing that I'm interested in doing is sort of moving beyond this correspondence between minimal surfaces and entanglement to other things, to other structures. So other space-time structures beyond minimal surfaces. And in particular, as we'll see, the corresponding thing will be other entanglement structures like beyond bipartite entanglement. So things like tripartite entanglement and so forth. Okay. Okay, so some motivation. So black holes, we know they exist in our universe. We don't exactly know how to describe them quantum mechanically. But one thing that we do seem to know, which is kind of amazing and still mysterious, is some entropy. So this is called the Bekenstein-Hawking entropy. It's given by the area, sort of natural units where I set h bar and c to 1, divided by 4g Newton. So really, it's the area in Planck units. So it's the area of the black hole. This is the area of the horizon. Of course, this is a real black hole picture now. And this is roughly where the horizon is. And so now associated to that horizon seems to be some entropy. Of course, when we have an entropy, then we have microstates, or we expect to have microstates. We still do not understand what these microstates are. It's important to say, but trying to understand what they are, we're going to learn something new of quantum gravity. In particular, yeah, so an understanding of these microstates requires quantum gravity. Now, black holes, we know, they carry entropy, but they're really thermal objects. They have a temperature, there's the Hawking temperature. And so, you know, if we have some thermal environment, it's useful to introduce some density matrix, which is a thermal density matrix like this. Microscopic theory. So again, you know, we don't really know what the microscopics are, but we expect something like this to be true. Now, when you have a mixed state, it's a density matrix, it's useful to think about purifications of it. In particular, there's a natural purification called the thermophile double. Essentially, what you do is you take two copies of your Hilbert space, of your black hole Hilbert space. So that's black hole, tensor black hole prime. You think about a maximally entangled state on that system, and then you apply the density, or the square root of the density matrix. So basically, this is pure state where if I trace over BH prime, black hole prime, I get back this mixed state. Okay, so that's a very natural thing to do. It turns out that once you look at this state, there's a very natural candidate for what describes this state. And in particular, you know, this is some idealization of the black hole, this density matrix. And in reality, you know, maybe it's not even a mixed state, maybe it's a pure state that looks sufficiently random that it looks like a thermal state. But similarly, there's an idealization of a hole called the Schwarzschild black hole. And the Schwarzschild black hole has this amazing fact. You look at its a time slice, and, well, then naturally there's two universes. There's a universe. In particular, this here, this line here is the event horizon. And to get to the universe prime, you have to move in a spatial direction, right? Space-like direction. So it's very natural to try to associate this thermophile double state to this we can't hear.
No, it's very hard to listen, to hear you, okay?
Try to look at my screen. I think that's the key.
If you can, when you look at the screen or stay close to the screen, like where you are, then it's much more clear. When you walk back and forth a bit, it becomes very difficult. Also, the question I have is, are we supposed to be able to see, it looks like you're using a pointer. And
Yes.
I am not able to see in the slides where you're pointing. So if I'm supposed to be able to, if someone could let me know what I'm supposed to do, or if you could try and verbally describe the area on the slide you're pointing to, I'm very interested in what you have to say. I'm just not able to see or follow. There, that's better with the mouse.
So this is what I'm going to do, and this is going to solve both problems. So very good. So you can see my mouse, so that'll do. Okay, so all right, so it's natural state, this purification of this density matrix, and this somehow corresponds to this maximally extended Schwarzschild black hole. In this setting, the black hole entropy that we talked about is an entanglement entropy. It's what we call an entanglement entropy. It's something that measures the entanglement between these two systems, black hole and black hole prime. You know, one way to think about it is, well, one way to define it is to find the reduced density matrix for this state, which of course is this state by definition, because it's a purification, and then compute its von Neumann entropy, which is just the trace minus trace row log row. Okay. But the important thing here is we've sort of replaced the black hole entropy with an entanglement entropy. And now, if you look at this sort of space-time, it turns out that this surface here is a minimal surface. This red surface here, which is the black hole horizon, is a minimal surface. So there's some correspondence between minimal surfaces and entanglement. Now, generalizations of this area entropy relation can be extrapolated away from black hole physics to general facts about quantum gravity. There's sort of a vague proposal that goes under the name of the holographic principle, which basically says that if I have some region in quantum gravity theory, then the maximum amount of quantum information is bounded by the area of the boundary of that region, which is kind of strange from a point of view. If you think about just a non-gravitational theory, usually you would think about the entropy as bounded by the volume of the system. So this seems to be true. It's a little bit vague and hard to make precise. There is a precise version of this, which relates to what I just told you, which is whenever you have some minimal surface in your quantum gravity theory, there seems to be some entanglement entropy associated to it. And it's the entanglement between the inside and the outside of this minimal surface. So here's a minimal surface, there's entanglement between these two, and it's measured by this sort of the area of this minimal surface. This is the proposal of Ryu and Takinagi. Now, one way to make this really precise is to think about a certain class of quantum gravities. They're not exactly our universe, so they're not really the thing that we're interested in, but they're toy models, and they can be studied as theories of quantum gravity, and they, we can study holes in them and try to understand the black holes in these theories. So the name of this goes under the name of ADS-CFT, or the holographic correspondence. It's a conjectured exact duality between a quantum gravity theory and some space-time. The space-time is sort of negatively curved, hyperbolic space, and this is an Escher picture of hyperbolic space. And inside here, you think about space-time is fluctuating. There's some quantum gravity theory in here. And then on the boundary, nothing is fluctuating. And in particular, you can think of it as there corresponding a dual quantum field theory on this boundary. So, again, you should think about, you should think of this quantum field theory as just quantum mechanics with many degrees of freedom, describing all the degrees of freedom on this boundary. And this duality says that there's some exact correspondence. So in particular, the Hilbert spaces should be the same, the observables should be identical, and so forth. It's a beautiful duality, definition of quantum gravity. So we can use it to study things like black holes. But again, it's only a toy model. Some aspects of the dictionary. To make sense of it, you need the quantum field theory. Well, for the duality, you need the quantum field theory to have many degrees of freedom per site. So you think about many fields or something like that. And in which case, the Newton's constant is inversely proportional to that number. So you want Newton's constant to be weak so that the quantum gravity is not out of control. Another thing that you find that this curvature in this spacetime has a very long distance scale. Then if that's the case, then in the dual quantum field theory, you find is strongly interacting. It saturates scrambling and chaos bounds. So it's something that we can use strongly interacting theories. Now you can study things like, as I said, I alluded to, you can study non-trivial backgrounds. The original space that I drew is this hyperbolic space, but you can put a black hole inside that hyperbolic space by taking the quantum field theory on the boundary and heating it up. So then you have a thermal state in the boundary, and in the bulk it corresponds to a black hole. In this case, we have an exact sort of understanding, or in principle, exact understanding of the microscopics of that black hole. The entropy is precise, again within principle known microscopics. So on the boundary, I can take my quantum field theory, I can think about a state in that quantum field theory, and I can split the state into, say, I think about the quantum field theory as having some tensor factorization between A and B, and then I can produce a reduced density matrix on A, and compute its von Neumann entropy. And Ryu and Takinagi taught us that that actually corresponds in the gravitational theory to to some minimal surface computation where you look for a soap bubble that ends on the boundary, it falls into the bulk under the force of gravity. So it might, I'm going to use sort of standard language. This is the bulk of the space-time. Okay, good. So, the basic motivation of what I'm getting at, the together, at least in this duality. So maybe that's a principle that we can extract from this duality and use in our own universe. And is entanglement really enough? Maybe there's other things that we can study. In particular, minimal surfaces are not the only geometric quantities that you can think about in the bulk gravitational theory. We don't have, it turns out that, if we, as I alluded to, in principle, we have some control over the microscopics. In practice, it's very hard. And in particular, for general quantum gravity theories, we do not have control over that. So what I'm going to do is I'm going to replace this hard problem with an easier problem. So this is like a toy model of a toy model, where I'm going to study something called a random tensor network. And in particular, this random tensor network, you don't have complete control over the microscopics, and it has this same area entropy relation. And so then I can ask, in this model, is bipartite entanglement enough? Can I get other things out of the random tensor network? Okay. Yeah.
You're mute again.
Asking a question. So the question was, what do I mean by the glue that binds space-time together? Good question. I don't really know, and that's sort of the research program. Well, what do we mean by that? The basic idea is that there is this correspondence between areas and entanglement entropy, and there's some sense in which that's a universality of various things. So in gravitational theories, gravity is universal. It's something that couples to everything. And in quantum mechanics, entanglement is universal. It can be, all degrees of freedom can be entangled with other degrees of freedom. So there's some universality to this, and so it seems like these things are connected in a way that we should really understand.
There is a question. I have a question. You mean universality or you mean generality?
Say it again?
You mean universality or generality?
Say universality.
Well, universality is very precise. It means that it's independence of the short distance definition of the theory. That's what universality means.
Sorry, Eduardo, I just forget when I said universality. What was it in context? In context?
Yeah, I want to understand the context. That's precisely the problem. Okay.
If I say universality again, I'll try to think about what I'm saying.
We call it the universal law of gravitation. This is fine in a classical sense. But I'm not sure that once quantum mechanics is thrown into the mix. So
I say universal in a different. Okay. So toy models, these tensor networks. So the building blocks of tensor networks are kind of basic. They're just sort of graphs with lines coming in and out. This audience should know some basics about tensor networks. In particular, a quantum circuit is just a tensor network, where I think of time as going up in this picture. And then I have some Hilbert space on the Hilbert spaces on the bottom here. There's some unitary operator that acts here, and then I get some output here. So in this sense, this box here is representing an operator. It's an operator acting on this Hilbert space, which is a tensor product of the Hilbert space of these three legs. We can think about states in this sort of pictorial description. I'm going to draw these as triangles. This is a pure state, or a vector in the Hilbert space. This is a wave function in this Hilbert space. And so, for example, I can take this operator and compose it here, and I'll get some output here. which is again a state, a vector in the Hilbert space. Now, one thing that's useful with sort of these tensor network pictures is we're going to have these lines running everywhere, and we're going to be manipulating these lines. And there's a really sort of beautiful idea. Just take, if I think of time as going up, and I have just a line like this, it's something that does nothing, right? It's a circuit that does nothing, so it's the identity operator. The identity operator. But then if I take this line and I bend it around like this, or equivalently, if I think of time as running from, if I think of space as running from bottom to top, then this turned around actually looks like a space. It happens to be unnormalized, but that's not a big issue for me. So this is an example of a wave function maximally entangled between a Hilbert space and some other Hilbert space, H prime. This looks very much like this correspondence between the Thermofield double that I just discussed. Okay, so given this structure, we're going to start building wave functions based on tensor networks. I'm going to follow the construction in this paper called the random tensor network. And the idea is that we start. The graph has vertices and edges, and so this is a picture of my graph. And associated to various elements of this graph, we'll try to construct a wave function. In particular, there's going to be boundary vertices. These are the ones that I have drawn as white dots here. And you should think of the wave function as living on these boundary vertices. Very much like the duality of ADS-CFT, where you have some boundary Hilbert space. I'm going to have some circuit that looks like this. So I have some fiducial state, and then I have some unitary. This unitary is going to be a random unitary. I'm going to pick it from the Haar ensemble, which is sort of a uniform ensemble on all possible unitary matrices. And then the output is going to be fed into the edges. So this is a vertex. The output is going to be fed into the edges. On the edges, the edges are just going to contract between the different vertices. But one way to think about that is to turn this picture, sort of deform this picture like this. So the edge runs like this. And then if I think of time as going up, then this thing here looks like a state turned around. So it's like a bra. And so I'm taking some I'm just applying that bra to the wave function, or in other words, I'm making some projective measurement on this maximally entangled state. And finally, as I alluded to, the vertices, which are these dots, these white dots, I'm going to do nothing. So at those vertices, I'm just going to have dangling edges, and that's where my Hilbert space lives. That's where the wave function lives. So I put it together, and I get some wave function that's described by this equation. It's basically these random unitaries applied on the vertices, and then I'm projecting onto this maximally entangled state on the edges. And the result is some wave function on the boundary. Now, this wave function has sort of interesting entanglement structure. In particular, its entanglement structure will look a lot like ADS-CFT. So it's sort of a toy model of ADS-CFT. A nice feature of this model is that it allows us to compute various things. In particular, this Haar ensemble allows for computations of entropies using statistical mechanics models. A concept that you're probably well familiar with, various colloquia and so forth have discussed this. Precisely, you can build something that looks a lot like ADS-CFT by picking a graph, this graph to begin with, as a hyperbolic graph. Something like this. A hyperbolic graph would go off to infinity. It would have infinite number of edges and vertices. We cut it off in some way, and then we put it. So at the end of the day, this graph describes a wave function on the Hilbert space of the tensor product of all of these boundary edges. Okay. It's only a wave function. It's not really the complete theory or anything. That's why it's like a toy model. In particular, there's no Hamiltonian, there's no dynamics. It's just a wave function. But that's okay. That's enough for us to compute entropies about that aspect of the duality. Or really the entanglement entropy of some partition of these boundary indices. So we have these these boundary vertices. So we had these white vertices. That was the boundary, and we're going to split it into two sets, A and B, and we'll think about the entanglement between A and B. Right. So this network describes a pure state on this boundary. When I reduce on A, it's going to be a mixed state. Okay. Interested in the von Neumann entropy of that mixed state. You can do this, it turns out, computations. In particular, it's sufficient to look at something called the second Renyi entropy. So the second Renyi entropy is some generalization. Okay. See the chat so I can respond. And how do you do this? Let me just run down of how you do this. It's a little complicated, but the basic idea is that you take this density matrix over n as 2. You have 2 copies of this density matrix. Each density matrix has 2 copies of the wave function. So you basically have 4 copies of this tensor network. At each vertex, you're doing sort of a higher average. So this is just a picture of one of the vertices. And so we have 4 copies here. When we average over these unitaries, we get various contractions from this network. You can think of this as some kind of width contractions. And you can think of this as some width contractions. And for n as 2, you just get 2 possibilities. You get this sort of straight through identity or this crossing permutation. Okay, so these 2 options at each vertex mean that the result, you're summing over all of these possibilities. The result is some kind of effective classical Ising model where you have a spin degree of freedom at each vertex. And that spin is telling you which version of this contraction you're doing. Okay, so then we get some Ising model on this graph. And the Ising model can have values +1 or -1. Is weighted by some free energy, in this classical effective Ising model. It turns out that this free energy wants the spins to align. So it looks something like this, the difference in the spins on each edge. So it wants spins to align across each edge in the graph. Now, at large bond dimension, the effective temperature goes to 0. This becomes very big. Inverse temperature. So this is what I should have mentioned, that these graphs have bonds in them with some Hilbert spaces. Each line in the graph is associated to some Hilbert space, and there's some dimensionality of that Hilbert space, and I'm going to keep it fixed for each of the bonds, and I'll call it chi, and I'm going to send that to infinity. And that's kind of like taking this G Newton to 0 limit in the duality. So that's where we get useful things. So the spins want to align, and so that means in this limit, we get domain wall configurations. These domain walls want to sit on minimal cuts in the graph. What is a minimal cut? Well, it's kind of simple. It's basically a cut between the 2 boundary regions, A and B. So here are my 2 boundary regions that I'm picking. And I'm trying to find a cut through the network that removes the edges and divides the graph into 2, where one part of the graph has A. I can do that in many different ways, but there's a minimal one with the least number of cuts at the edges. And in this graph, it's just 3 cuts. And so the domain wall sits on this minimal cut, and it computes the second Renyi entropy. And in particular, it's this minimization formula, which looks remarkably similar to the minimization formula of real Entanglement. Now, I did this for the second Renyi entropy. You can do it for any of the Renyi entropies as long as it's an integer Renyi entropy, and you find the same answer for each Renyi entropy. That actually means that you can extrapolate it back to the entanglement entropy. Okay, so then this works. There's an interesting dual description of this minimal cut in this network. Through the network, but some flow of some conserved quantity through the network. We have a source and a sink. So my source in this case is A and my sink is B. And I'm trying to send some conserved quantity through the network from A to B. And I impose some capacity limit on each edge. And in particular, because all my bond dimensions are the same, it's the same unit capacity limit on each edge. And then you try to maximize that flow, right? So I could put very little through that, that's okay, but there's some maximum flow that I can get through this network. Of course, the maximum flow is constrained by the bottleneck, which is the minimal cut. And so this famous max cut min flow theorem says that the minimization of the area of a cut is equal to the maximization of the flow between A and B. Okay, so this is kind of interesting rewriting of this area formula. In particular, it seems to be giving a vivid picture, representation of the entanglement in this wave function. If you think of the flow as being associated not to some conserved quantity, but to entanglement itself. So each of these flow lines somehow corresponds to some EPR pair or Bell pair, or some number of Bell pairs. So somehow it's representing the distillable entanglement in this wave function. And so we replace it by these EPR pairs. And so this is such a nice picture that these authors took it and applied it to quantum gravity directly, not within this tensor network picture, but in quantum gravity. And in that language, you can describe minimal areas in a dual language in terms of something called bit threads, which are these divergence-free flows in your space-time, which have some bound on the number of flow lines that you can have, on the density of these flow lines. And again, you find that the maximum flow is governed by the bottleneck here, which is the area of this minimal surface. Now, given this picture, these authors, in particular, we're going to start thinking now not about bipartite entanglement, but what can happen when we have three parties, so A, B, and C. So I've got A, B, and C here. Instead of B being two boundary vertices, I now have A, B. I've split it into two. So I have A, B, C. And to each of these regions, there's a minimal cut in the network, right? So which in this case, bipartites the boundary, partitions the boundary between B and AC for that minimal. Well, this minimal cut here partitions the boundary between C and AB. Okay, so the minimal still computes the entropy, but it turns out that you can find a flow network that also computes the entropy. This flow network is a little bit more complicated now because we can have flows between two different sources and sinks, or sort of many various combinations of sources and sinks in this network. So this goes under the name of a multi-commodity flow. But it turns out that there's a flow that exists, flow out of each terminal computes its entropy. So this picture, the very existence of this picture for three parties suggested to these authors that the entanglement structure of these wave functions, and maybe in quantum gravity, is very, very special. In particular, it looks like we can replace these flow lines with sort of EPR or Bell pairs. And the wave function suddenly looks like just a whole bunch of EPR pairs shared between pairs of these A, B, C regions. In particular, a structure like this, a wave function like this, has no tripartite entanglement. by definition, right? So tripartite entanglement is something that goes beyond entanglement like this. It can't be written as sort of bell pairs between pairs of the parties. Okay, so that was the conjecture based on this flow network. It turns out that this conjecture, which was dubbed bipartite dominance, is wrong. It's wrong for high random networks, and very likely also wrong for quantum gravity. Like in this paper. To see this, these authors actually used a quantity that goes beyond entanglement entropy. It's a quantity that I actually defined with an old student called reflected entropy. And we introduced it in the context of ADS-CFT, but then we studied it, outside of ADS-CFT. And it's kind of a new quantum information measure that has some interesting properties. And it has had, since we introduced it, has had sort of many applications. I think one of the biggest advantages of this quantity that we defined, and I'll get to it in a second, is that it's something you can compute a little bit like negativity, if you know what that is. Okay, good. So one interesting thing, this is a side note, but I think it's kind of interesting, is that this bipartite dominance conjecture turns out to be correct if you don't use high random unitaries in your circuit, but you instead use something called a random stabilizer state at each vertex. So random stabilizer states are things that you can sort of efficiently simulate on a classical computer. So there's something that are less chaotic than high random states. And so, it's interesting that those random stabilizer networks actually satisfy this bipartite dominance conjecture, but the high random ones do not. So somehow this is telling us something about the chaotic nature of quantum gravity. Okay, so reflected entropy is very quickly, and then I'll I'll say a little bit about how to compute it in this random tensor network and how it tells you that this bipartite dominance is wrong. Okay, so the reflected entropy is defined given a mixed state on two parties. So just any mixed state rho AB with two parties. Then there's some entropic quantity associated to it that's new. So the idea is to think about a canonical purification. This is very much like this thermofield bubble that I talked about for the black hole. As follows: given a Hilbert space HAB, I can think about the Hilbert space, an associated Hilbert space, which is the Hilbert space of matrices. It turns out that this can also be thought of as a tensor product of the original Hilbert space with a double copy, where the second copy is the dual Hilbert space. Okay, so this is basically a doubling procedure. We take our original quantum system and we double it in some canonical way, and there's some canonical purification in that doubled state. And then associated to that canonical purification, you can compute another von Neumann entropy, where we split the parties into, well, there's four parties now, A, B, A star, B star, and we split the parties into A star, and we compute its von Neumann entropy. Okay, so the reflected entropy satisfies some interesting properties. One of them that we're going to use today is that it's bigger than the mutual information. So the mutual information is defined in terms of von Neumann entropies between the two parties, A and B, in this way. And it's a measure of classical, it's just a measure of correlations in any correlations in this state. The fact that this is bigger than the mutual information sort of seems to suggest that the reflected entropy is also a correlation measure of that. Okay. Now, there's another related quantity, was defined in the quantum information literature, called the entanglement of purification. And the idea here is that instead of taking a canonical purification, I take any arbitrary purification, and I compute the same sort of entropy, this AA prime entropy, and then I minimize over all possible purifications and all possible purifying systems. So this is the entanglement purification. It has sort of operational interpretation in quantum information, it really is a correlation measure. It's a total correlation measure of classical and quantum correlations in the mixed state. It turns out that there's an intimate connection between reflected entropy and entanglement of purification. And in particular, there's this outstanding conjecture in random tensor networks that up to a factor of 2, they're the same, plus small corrections. The interesting thing about this is that one is seemingly much easier to compute than the other. This is a much harder quantity to calculate because I have to minimize over all possible purifications. Okay, so now it's interesting to consider the difference between these quantities. So the reflected entropy minus the mutual information. So I remember I told you that, yes, question? So remember I told you that the reflected entropy is bigger than the mutual information. So if I take the difference, this is a positive quantity, a non-negative quantity. So it turns out that this difference is a certain measure of a kind of tripartite information in the following sense. So in particular, you can prove, these authors proved a structure theorem that showed that if this quantity vanishes, then any purification of this two-party system, AB on 3 parties, ABC, has the following form. If you ignore what I've written here is a state that looks exactly like this bipartite only state that I drew before. So let me go back to that picture. So this is a bipartite only state. And so without the sum, it looks like the state is just one without any tripartite information. However, it does allow for this superposition of these kinds of states as long as they're orthogonal to each other. So it's a superposition of bipartite only states. It still allows for some kinds of tripartite states. For example, the GHC is a classical example of a tripartite state, which is just this state on qubits, on 3 qubits. And in particular, this state has vanishing G. So this G quantity detects some forms of tripartite information, but not all. In fact, these authors also showed that if I replace SR with EP times 2 in this and define a related quantity, then in fact, if that vanishes, if and only if it's exactly a bipartite only state. So in some sense, the entanglement of purification used in this way does better than the reflected entropy of detecting tripartite information. But because one is easy to calculate than the other, we're still going to learn some information from the other. Okay, good. So this GAB quantity was dubbed the Markov gap by these authors. This name Markov gap is a little bit loaded. Basically, it comes from the fact that the bound on reflected entropy being positive follows from a quantum information inequality called strong subadditivity, which is super important. States that saturate strong subadditivity are called Markov states. It turns out that if you translate that Markov condition in terms of this sort of reflected density, this canonical purified density matrix, it turns into this statement. So you can sort of think of this as some kind of a Markov state. So that's why it's called the Markov gap. Okay. The conclusion is that if I can find states where this quantity is non-zero, or a conclusion is I find states in particular, if my random tensor network that I'm studying at large bond dimension has a non-zero Markov gap, then we can be sure that it's not close to a state which is a sum of these bipartite only states. So that suggests we should calculate reflected entropy in these random tensor networks and check whether this quantity is 0 or not. So that's something that we did. This paper, the computation is much more involved than the one computing the Renyi entropy, just the Renyi entropies, but it's still doable. Basic idea is you have to do something called a replica trick. You have to replicate twice. Basically, we want to compute something about this canonical purification, which had this square root in it. So what you do is you take the square root, you turn it into some integer power, and then you try to get the answer and analytically continue the answer back to the square root. Okay, and so that, this is often a heuristic. It's a heuristic thing that we use. However, it turns out that it can be made rigorous in certain situations, and this is a situation where you can make it rigorous. Okay, so once you do that, you end up with a much more complicated stat-mech model where the spins are replaced by elements of the symmetric group SMN, and so there's many elements here. But so it's complicated, but it turns out that you can distill a much simpler answer out of it. It turns out that you can prove the answer is independent of this new parameter M, and it's dominated by one of three possible spins. So it becomes an effective ising model with three flavors. So I'll call these three flavors A, B, and C. And in particular, there's boundary conditions on this ising model, which is fixed by the boundary regions A, B, and C. It's fixed by the fact that we're computing this reflected entropy. Okay, good. Okay, so now we're looking for some more complicated ising model, slightly more complicated ising model, where we have three flavors. And in particular, this allows us to have something called a multi-way cut. In particular, now, instead of having a cut through the network, which sort of bipartites two different kinds of spins, now we need three cuts that partitions the network into three kinds of spins, A, B, and C. The boundary conditions dictate that the B region, little b region has to contain big B, the little C region has to contain big C, and the little a region has to contain big A. So the answer for this reflected entropy is determined by this multi-way cut. In particular, it's this multi-way cut minus a regular cut. Now it turns out that computing these multi-way cuts in just in some general graph is actually quite a difficult thing. It's an NP hard problem. This is a statement that I don't know really what it means. It's an interesting fact. Geometries, where we have three regions now, and they leak into the bulk like this, and they join at some covalent vertex. So this is this hyperbolic network, and you can extrapolate this answer also into ADS CFT, and you guess that this is computing something like this. So given this structure, you can compute the Markov gap, and if the tri-way cut that I'm describing here is non-trivial, i.e. it does have one of these non-trivial trivalent vertices in it, then the Markov gap is positive. In particular, the Markov gap per unit quantum dimension is positive. So that suggests that these states, that proves that these states are actually not these bipartite only states. Okay, and there's analogous results for general graphs. Okay, it went pretty fast. I'm going to conclude that bipartite entanglement is intimately related to minimal areas in quantum gravity, but there's a lot more to geometry than just minimal areas. And in the same token, there's a lot more to entanglement than just bipartite entanglement. So these multi-way cuts that we're finding here sort of probe a new geometric structure in the bulk, and they correspond to some new measure of tripartite, at least in these random tensor networks. So there's many open questions. There's a question of can we prove this? Or the statements here are rigorous that I'm making, but they're rigorously made in the context of these random tensor networks. Eduardo has a question.
Yes, about your three-state model. This
Yes.
is reminiscent to a Potts model on a graph. And there is a well-developed theory in statistical mechanics of so-called chromatic polynomials on graphs, which are, have quite a rich structure. And I was wondering whether this has any connection with it.
Yeah, it's a good question. I don't know. Is that the tensions I didn't actually mention? The tensions of the domain walls are not the same. So there's three flavors and there's some tension. They're not the same. It turns out when n is 2, this is the Renyi parameter, n is 2.
Yeah.
The tensions are the same. So yeah, maybe it's exactly the, I wonder if it's related to this Potts model. Certainly, the other thing is that we're interested in it in the sort of small temperature limit. So that's where you get these domain walls that dominate. And you can make these statements about multi-way cuts.
Mm-hmm. I mean, these models actually have a very rich structure of states in particular. So that's why I was wondering whether that's important or not.
One thing to say is that our results are only relevant at very large bond dimension, because at finite bond dimension, it's a much more complicated model. It's not, it wouldn't be this Potts model.
Okay.
Because the actual general spins are much more general.
Yes.
So I don't know. Some important structure, but I don't.
That's a question. That's all. Thank you.
Yeah. Okay. So, right. So this bipartite entanglement is intimately related to these minimal surfaces, but there's more to geometry than that, and similarly, there's more to entanglement than just bipartite entanglement. And yeah, so the multi-way cuts are some new structure, a new geometric structure, and yeah, really interesting to study. Yeah, so it's an interesting question to study this in gravity, to try to prove these statements rigorously in gravity. What is the structure beyond 3 parties? Can we relate this to entanglement of purification? I've only computed this reflected entropy, but there's open conjecture about entanglement of purification. Yeah, so many questions, and let me leave it there.
Can I ask one more question? Hello?
Yes, Marius, yeah.
Okay, good. So you have this, sorry if I went ahead of Douglas. So you have these nice examples of this implicitly tripartite, interesting partition, right? Configurations, right, where you have this gap. Are these configurations which are even, they're now constructed using hyperbolic geometry, but shouldn't there be some kind of small models for this? I mean, small dimensional models, or do you have to go to the limit to write some interesting new states which satisfy this gap?
Oh, no, in fact, a single tensor does this. So you just need a single vertex with 3 lines coming out of it, and that state corresponding to that, which is just a random unitary acting on 3 tensor product of 3 Hilbert spaces. That state actually has a non-trivial Markov gap, and you can prove it.
And then you can show that these simple tensors are actually contained in your hyperbolic picture, is that right?
That's sort of the irreducible structure here, but I don't know exactly how to extract that.
Okay.
Yes.
For other people who raise their hands, but I can't see who.
Okay, let me address this garbage in, garbage out. Absolutely no empirical.
I'm not sure you want to address that, Tom, but
Address the other people reading it and saying that I completely disagree with all of these statements.
Tom, stepping back before the tripartite entanglement, have you or has anybody else thought about the entanglement of formation and whether there's any bound entanglement before you get to the 3 parties?
So certainly, people, there are some conjectures about various forms of multi-partite, of mixed state entanglement, which is the subject of entanglement formation. It's a little harder because that quantity is hard to compute. So what usually people do is they replace it with negativity, which is something that can detect entanglement, but if it vanishes, you don't know if there's entanglement or not. So it's not a faithful measure of entanglement, but it's computable. So people have calculated that quantity. The interesting thing about it in these networks is that you can do the same things that I told you for that quantity, but it turns out to not tell you anything more than you always get a mutual information, which is something constructed out of minimal cuts and minimal error. So it really seems like you have to go to this reflected entropy to see this this tripartite structure. I'm not sure what.
Yeah. So I was just wondering whether the reflected entropy would help to get around the zero and the negativity. It doesn't see bound entanglement.
I don't think. I think it will have the same sort of issues because it's computable. Right? So we sort of know that. I think we know that faithful entanglement measures are very hard to calculate. Sort of issues, but yeah, I mean, it was a little bit better in this situation.
Okay, thanks.
One more question.
Yeah. Yes.
I think you said there was data lots of networks, and that was related to the fact that they're.
Yeah, it's a good question. Yeah, let me to the footnote. Yeah, so it's true that that you can do these calculations in random stabilizer networks, and you find that you can actually just prove that this structure theorem directly, that you get these bipartite like states, at least at leading order in large bond. Now, one interesting thing about these random stabilizer networks is that they're at most what's called a unitary 3 design, I think something like that, which means that they agree with moments of the Haar ensemble up to the third moment. So I'm using the Haar ensemble, but you can think about it, and it's clear that we're using more than the third moment. I mean, it's true, we're using more than the third moment. But it's natural to ask what kind of design is important for this structure. My suspicion is it's a 4 design. You'll get a non-zero, non-trivial Markov gap if your ensemble is a 4 design. That's a conjecture, but yeah. A multi-partite entanglement is a complicated game. So yeah, I don't know. I think it's for me. It's not something that I went into this thinking about, but it came out of it just because of this result on 3 parties. So maybe we can try to think about 4 parties and so forth. But I don't have any statements.
Hey, I have one other quick question. In terms of, instead of going to more parties, the other direction is going to, different dimensions instead of qubits, qtrits, and qdits, and also continuous variable entanglement. I'm just wondering if there's any connection or extension of those in this particular picture.
So, I'm thinking about, at least in terms of the networks, as each of the bond has some random dimensionality, some dimensionality which is in the end taken very large. So I'm working beyond qubits. So I know that beyond qubits things get way out of control in terms of multi-partite entanglement. But I'm not trying to make a general statement about it. I just some small statement. Yeah.